Imagine a bridge connecting Earth to the moon. It sounds like science fiction, but what if we paused and gave it serious thought? To build such a bridge, we would need materials far stronger and more specialized than anything humanity has developed so far. Earth's gravity, the moon's orbital motion, and the vacuum of space all pose immense challenges. Yet with advancements in nanotechnology and space construction, the idea may not be entirely impossible. But how could we align the Earth and moon to make a bridge even feasible? Did you know we always see the same side of the moon from Earth? This is due to tidal locking. The moon's rotation period matches its orbital period around Earth. Thanks to this predictable rotational alignment, we can design orbital docking schedules that take advantage of the moon's consistent orientation toward Earth, even as its position shifts. This is a highly favorable condition for future space bridge operations. However, the moon doesn't orbit in a perfect circle. Its orbit is elliptical, with a closest distance, perigee, of about 363,300 kilometers, and a farthest point, apogee, of about 405,500 kilometers. The average distance is around 384,400 kilometers, resulting in a variation of over 42,000 kilometers. This is what causes the supermoon, when the moon appears larger and brighter in the night sky. Because of this, a fixed-length bridge is physically impossible. We would need flexible, extendable structures and adaptive docking systems, or stop the bridge near the Earth-Moon Lagrange point, L1, where gravitational pull from Earth and Moon balances the orbital inertia. From there, transport pods could float freely using minimal energy, so whether by docking or free-floating, this segment could offer both technical feasibility and an unforgettable zero-gravity experience. Now imagine a future transport pod. Instead of being launched explosively like a rocket, it travels smoothly along the bridge at a constant acceleration equal to Earth's gravity, 9.8 meters per second squared. In theory, this means it could reach the moon in just about 36 minutes. Even better, inside, passengers live as if they're still on Earth. No extreme G-forces, no astronaut training, just a calm and comfortable cruise through space. This changes everything. If no intense training or physical qualifications are needed, millions of ordinary people could explore space. So here's the big question. How much would it cost? If countries and private companies invest steadily over decades, and if we build a reusable infrastructure with two-way transport pods, automated stations, and a high-capacity system moving hundreds of thousands of people annually, combined with energy-efficient travel using gravitational balance zones, could a round trip to the moon be possible for around $20,000 per person? Maybe it's not just a fantasy. After all, it's a chance to float in zero gravity, walk on the moon, and gaze back at Earth from space. Still, many technological challenges remain. What will power these pods? Nuclear fuel? Solar energy? Where do we source materials for a 400,000-kilometer megastructure? How will we connect and construct it in microgravity? Environmental impact must also be considered. A bridge piercing Earth's atmosphere might disrupt weather, animal migration, or ecosystems. In space, we must also face solar radiation and space debris. Protective technologies must evolve alongside the structure. But imagine the upside. If such a bridge becomes reality, the moon could be a tourist destination, a supply depot, or even home to a permanent human settlement. It could become a gateway to Mars and beyond, the birthplace of a new space economy built on curiosity and cooperation. And finally, the ethical question. Should we build it at all? Who owns the moon? Can we develop space responsibly without repeating our mistakes on Earth? For now, it's just a vision, but every reality begins as a dream. To observe, to question, to imagine. These are the roots of all progress. Imagination creates reality. Thank you.